Hi, I'm Nikita Cole from JetBrains, and today I present our work on multi-queue-based priority schedulers. This is a joint work with Anastasia Postnikova from ITMO University and Georgi Nadiradze and Dan Stark from IST Austria. First of all, let's discuss when do we need priority schedulers. In brief, we need them for iterative algorithms, such as parallel graph algorithms, parallel Dijkstra, parallel A star, BFS, Borovka, for Delaunay triangulation and PageRank algorithms. In all these algorithms, we do need efficient priority scheduler implementations. To give more insight on how parallel algorithms work, let's discuss the parallel Dijkstra one. Let me remind the sequential algorithm. We have a global queue, and at the start node to this queue, it's initializing the distance of this start node with 0. While the queue is non-empty, we extract the node with the lowest distance and try to relax the outgoing edges, adding the corresponding nodes to the queue and updating the distances. Let's make this algorithm parallel. Essentially, we need to replace the sequential priority queue implementation with the concurrent one and run all the iterations in parallel in T threads. And this concurrent priority queue is the priority scheduler we are working on in this project. Importantly, we can't stop when the queue is empty because it will be empty right after the first thread removes the start node. But the whole graph is not processed yet. So we need to stop only when the number of nodes in the processing state is 0. That's what this change performs. The algorithm is correct, right? But is it really correct? Let's take a look. Here we have two threads, and each of the thread is performing an iteration during which it extracts the node with the lowest distance and relaxes all the outgoing edges. And the following interleaving is possible. So the first thread dequeues node U. After that, the second thread dequeues node V with the worst distance. However, the second thread processes this node V first because thread 1 and thread 2 are executing in parallel, and only after that the first thread processes its neighbors and adds them to the priority queue. Thus, it's not the Dijkstra algorithm anymore, because when the node V adds its neighbors to the global queue, it's not guaranteed that the distance to these neighbors is optimal, and therefore it's possible that we need to recount the distance. So the algorithm is the following. When we try to relax the edge, probably we already have some distance, but we can improve it. So we try to update the distance if it's lower, and if the relaxation was successful, we insert this node to the queue, maybe one more time. Here we come to the main trade-offs. In the sequential version, each node is processed exactly once. However, in the parallel version, nodes may be processed multiple times, optimizing the distance. So we win from parallelizing the iterations and can lose by performing additional waste work when processing nodes with a non-optimal distance. As many experiments show, we win much more than we lose. So, priority schedulers should be fast, should be scalable to efficiently parallelize iterations, and surprisingly, they should not be fair. Remember the interleaving when we obtained an inversion even with the strict priority queue algorithm. We can have this inversion independently on the fairness. So if our implementation of the priority scheduler is fair enough, slightly relaxed, but fast and scalable, this is much better. The state-of-the-art BMod schedulers carefully leverage this design. Essentially, they both maintain a set of bags for storing the tasks in a way so that each bag corresponds to a particular uh, priority segment of size delta. In case of a beam, this delta can be tuned, and in case of PMOD, this delta is adaptive, so PMOD merge and split bags depending on the current workload. As you see, they do not maintain strict order. Instead, they maintain an order which is close enough to the priorities, and the implementation can be really fast and scalable. So ABIM and PMOD show outstanding performance. There is one more intriguing design, the multi-queue. Essentially, we maintain multiple sequential queues guarded by locks, and when we need to insert a new task, we choose a random queue, try to lock the corresponding lock. If the lock acquisition fails, we simply restart, and if the lock is successfully acquired, we add the task to this sequential queue. Usually it's a DR heap, and after that we unlock the lock and complete. However, when we want to extract an element, we choose two random queues, and among them we choose the one with the higher priority and try to lock it. Similarly, if the lock acquisition fails, we restart. However, if the lock is acquired successfully, we extract the top element, unlock the queue, and return this element. The key feature of the multi-queue design is that it provides great fairness both in theory and in practice, and this is achieved by choosing two queues when extracting a task. Let's compare ABIM and PMOD schedules against the multi-queue. Here are three experiments. On the left, this is the parallel BFS algorithm on the rod graph. In the middle, you may find the SS&P algorithm, which is essentially parallel Dijkstra algorithm on the 2-bit network graph. And finally, on the right, these are experimental data on the A-star algorithm on the western part of the rod graph of the United States. We vary the number of threads over the x-axis, and the graphs on the top show the speed up compared to the classic multi-queue version executed on a single thread, while the graphs below show the work increase compared to the same single thread execution. Here we see the following. First, with the multi-queue as the priority scheduler, the amount of wasted work is much lower. It's almost zero on these experiments. At the same time, the multi-queue is not efficient, and iterations themselves are much faster with the ABIM and PMOD priority schedulers. So, here is the main question of this work. Can we achieve better results with the multi-queue design by making it more practical, more efficient, still maintaining the same fairness guarantees? Let's try. The first optimization we consider is task batching. Essentially, each thread is equipped with two additional buffers, buffer for insertion and for retrievals. So, when a thread decides to insert a new task, it inserts it to the corresponding buffer. And after that, when the buffer becomes full, all these tasks are inserted into the multi-queue in a single batch. Thus, we do not need to acquire logs and access the multi-queue on each insertion, we do this once per the buffer size. It's much more efficient. Similarly, we can do the same optimization for retrievals. We can retrieve multiple tasks at once, and after that process them one by one. Intuitively, we benefit from much less log acquisitions and much less cache misses. Of course, we also have lower contention as we access the multi-queue quite rare. However, with such optimization, we can't achieve the same fairness. Instead of the task batching, we can use another optimization, which we call temporal locality. Let's assume we have two threads and four queues in the multi-queue. Let these threads choose a queue which serve as the temporarily local queue so that all the requests, both insertions and deletions, proceed with this local queue, and this queue can be changed with some probability. Of course, it may happen that two threads use the same queue, but it's not likely to happen as we have more queues than the number of threads, and we choose the next temporarily local queue by random. So compared to the task batching, we win by providing better fairness guarantees. However, we need to perform log acquisitions and releases on each insertion and deletion, so it's worse. But remember that as we work with the temporarily local queue, these log acquisitions, log releases are much cheaper than in the classic multi-queue design. The last optimization we consider reduces the synchronization cost for NUMA systems. Here you may see a typical NUMA system with 4 sockets, and essentially we have sequential queues on each socket in the multi-queue. What we want to achieve is to lower the communication between nodes. So imagine we are on the CPU number 1 right now, and we need to choose a random queue. The idea is that we choose the queue from the same socket with the higher probability, and we never use the out of the socket queue as the temporarily local queue. We still can perform operations from it, but never keep it temporarily local. Thus, we reduce the number of out-of-socket accesses, but as in the previous optimizations, we lose some fairness. Let's take a look how these optimizations work in practice. So the MQ optimized and NUMA version is the version that is tuned so that all the parameters, the string probability, the buffer size are tuned, and we choose either the task batching or the temporal locality optimization for insertions, and separately for deletions we choose the best version. And here we see that when we apply all these optimizations, we achieve significantly better performance, and we outperform PMOD and ABEAM on 2 of these graphs. That's great, isn't it? What is also important, all these optimizations do not break theoretical guarantees on fairness. Here you can see the guarantees for the classic multi-queue on the top, the guarantee on the average rank and the maximum rank with the high probability, and also the bounds for the MQ optimized version. Probably you don't understand all these formulas, but trust me, it doesn't matter. What is important is that essentially these are the same guarantees, and in case of the MQ optimized algorithm, we just add some parameterization depending on the uh, choice and buffer size probabilities. We already have great results with these optimizations, but here's the question on the table: can we do better? And in short, the answer is yes. So, let me introduce a new algorithm, the stealing multi-queue algorithm. Essentially, each thread is equipped with a thread local sequential priority queue, and most of the insertions and extractions are performed with this queue. Importantly, these queues are not protected by locks, so we don't need to acquire the lock and to release it on each operation. However, to make the algorithm kind of fair, we need to synchronize threads. So, with some constant probability, we steal from other threads, and we steal in a batch. So, we steal multiple tasks. Um, for that, we also maintain a thread local buffer for these stolen tasks, and we process these tasks first when we need to extract a new task. Uh, let's try to write a pseudocode. So we have uh, an array of sequential priority queues, one queue per thread, and also thread local buffers for the stolen tasks. When we need to insert a new task, we always do this into the local queue. However, the delete procedure is more complicated. First of all, we check whether the buffer of the stolen task is empty, and if it's not, we retrieve the first task from the buffer. After that, if the buffer is empty, with the constant p steal probability, we try to steal tasks from another thread, and if the stealing is successful, we return the first task from the stolen ones. The rest of them are stored in the buffer, and if the stealing procedure is not successful, or if we decided not to steal, we work with the local queue. So we extract the top element from the queue, and if it's not presented, if it is presented, we return it, and if not, we try to steal again. The stealing procedure is straightforward. We simply choose a random thread and check whether its queue, the top element from it, is better compared to the top element in the local queue, and if it is better, we steal the specific number of tasks. If the stealing is not successful, we return null. That indicates that the stealing procedure fails, and if the stealing was successful, we add all the elements except for the first one to the buffer of the stolen tasks, and return the first stolen task as the result. So the implementation is simple, but we need to clarify how the add local, extract top local procedures work with our sequential priority queue, while we also have concurrent accesses with the top request and the steal function. In our paper, we suggest using DRE heaps with the special stealing buffers for performing stealings by other threads, and these DRE heaps are fast as they are sequential, so we can benefit from this, and the stealing procedure is kind of supported externally. So the structure is the following. Um, for each thread, we have a DRE heap. Also, we have a sequential stealing buffer of the specific size, and to synchronize accesses to the buffer, to synchronize the stealing procedure, we maintain the epoch counter and the storing flag atomically. And the list of methods we need to implement is now highlighted with red. When inserting a new task, we always add it to the local DRE heap. In addition, we check whether the tasks in the stealing buffer are already stolen by reading the corresponding flag and fill the buffer in this case. We'll discuss the procedure further. To extract the top element, we always delegate to the DRE heap. Let's now discuss how the top function, which can be invoked concurrently with the add local and extract top local requests, can be implemented. In our solution, we first of all read the epoch at the stolen flags, and we never access the underlying DRE heap. We always read the stealing buffer. So, if the tasks in the stealing buffer are already stolen, then we fail. However, if there are tasks that are eligible to steal, we did the first one, and this is the top element we return. Before that, we need to check whether the epoch is still the same. So we do this, and if the epoch has changed, we restart. If not, we successfully return the top element. The steal procedure is organized in a similar way. We first of all read the current epoch and the stolen flag, and if the elements are already stolen, we fail, returning the empty list. At the same time, if the elements are in the buffer, we read all of them in an unsafe way, so we don't care whether there are concurrent steal accesses. It doesn't matter now, because after reading, we check again whether the epoch is still the same, and the flag is set to false, and we try to make a cast by changing the flag if the epoch is the same. If the cast succeeds, we've successfully stolen the tasks, so we return them. Otherwise, we simply restart. Now we discuss how the fill buffer procedure works, and note that we invoke it only when the stolen flag is set to true. So we safely clear it, we fill it with the new elements, and at the end we atomically increment the epoch and reset the stolen flag. Let's check the performance improvement we've achieved with this stealing multi-queue algorithm. So here you see the classic multi-queue algorithm, our multi-queue optimized version, and the stealing multi-queue algorithm via DRE heaps and stealing buffers. And we see that the SMQ algorithm is significantly faster than both the classic multi-queue and its optimized version. The SMQ algorithm is parameterized with the stealing probability and the stealing buffer size, so we tuned both these parameters in the experiment. You also may notice that the work increase stays the same with all these optimizations, what is great. Okay, let's compare the SMQ algorithm versus the ABIM and PMOD schedulers. And here we see that it's much faster on the graphs on the left and on the right, and shows competitive performance on the Twitter graph on the SSP problem. We also added a special SMQ default option, so it's not tuned option. We've chosen um, some parameters, fixed them. I mean the sting probability and the buffer size, and we run all the experiments with the same parameters. So it's slightly worse than the tuned version, but it's still better than the tuned versions of ABIM and PMOD, which is kind of surprisingly. Importantly, the SMQ algorithm, as well as the optimized version of the multi-Q, provides the same theoretical fairness guarantees. So, let me make some conclusion. First of all, this work shows that the multi-Qs can be practical. We can apply the task batching, temporal locality, and NUMA awareness optimizations, and thus we achieve outstanding performance compared to the classic design and the state-of-the-art priority schedulers. Also, we've suggested a novel stealing multi-Q algorithm which outperforms all the existing solutions in many real-world scenarios. And the last but not least is that both the optimized version of the multi-Q and the stealing multi-Q algorithms provide theoretical fairness guarantees in a way similar to the classic multi-Q algorithm. I hope you've enjoyed the presentation, and if you have any questions, don't hesitate to contact me.